Good evening. I welcome you all for the Week 10 live interactive session for the course Polymers, Concepts, Properties, Uses and Sustainability. Now let's get on to the session. Let me share my screen. Okay. As usual, let's get on to the brief recap of lectures of Week 10. The lectures of Week 10 were on polymer processing and recycling techniques, which is in continuation with Week 9 lectures. So, lecture 70 was on polymer processing. It was on uses. So, here the lecture started with discussion on different shaping operations like extrusion dies, and then stretching operation, uh, and rolling and blowing operations. Then there was a quite a bit of discussion on blow molding operation as well. What are the different steps of blow molding operations? The next set of discussion were on time scales for polymer processing operation. Here, the cycle time for different polymer processing operations like injection molding, thermoforming, and rolling operations were all discussed. This was followed by what is the production rate uh, in polymer processing for different polymer processing were also discussed. The next set of discussion was on mixing in polymeric system. So what are the mechanism of mixing? There was a discussion on laminar mixing and dispersive mixing, and what are the mixing operations, and what are the mixing equipments. For example, Branbury mixer is used in polymer mixing. Okay, so these were all discussed in polymer processing lecture. So the next lecture was on flow simulations. So this was on uses again. So the lecture started with modeling of polymer processing operation, which is a multi-scale phenomena. So there was a discussion on continuum description where the overall macromolecular behavior or bulk scale behavior, where the macromolecules system is considered as a continuum. Okay, with infinite particles between each particles forming a continuous system. Okay, and what are, whether it is a single phase or multi-phase. For example, crystalline domains, amorphous domains, or polymer blends having two different polymer domains. So how are the continuum description in these things? And then there was a discussion on the molecular description. So this is based on molecules. So thousands of molecules. Okay. Uh, uh, there were discussion on this, and then the transport phenomena, especially in case of continuum descriptions. So what are the set of equations used? So you have mass balance, momentum balance equation, or energy balance equation, and then species balance equation. Whereas when you consider molecular dynamics, it is on solving the momentum balance, which is nothing but Newton's second law of motion. Okay, the momentum balance, because the molecules or atoms are continuously moving. Okay, so the momentum balance equation, which is what is solved in molecular dynamics. Next, what is the need for modeling and simulation? Okay, you have to design the process and optimize the processing condition. Okay, and then what will be the specification of the final product, and then what will be the microstructure of the final product. So these are the questions that leads to a requirement for a modeling and simulation. Okay, and then there was a discussion on mass balance equation, which is nothing but a conservation of mass, and then linear momentum balance, which is nothing but Newton's second law of motion, and then conservation of energy. And finally, there was a brief description on enabling of polymer simulations, where different simulation softwares, for example, finite element method, computational fluid dynamics, And then certain software specific to certain industries were also discussed. For example, in case of an injection molding, what kind of software is used, and then in all these simulation process, what are the rheological models do we have to consider? So those were given a brief idea, like Finney model. These were all given some brief idea in this lecture. The next lecture was on processing for recycling. This was on sustainability. So, what are the different recycling methods? Primary recycling, secondary recycling, and then recovery and conversion. And what are the targets in Indian National Resource Efficiency Policy? Okay. For example, 100% recycling of PET by 2025 is one of those policies. This was discussed. And then what are the operations before a recycled polymer is processed? Okay, so first of all, we get polymer from different sources. As we saw, it can be from different sources. So and it is of different sizes, and a different polymer mix you will get in. So you have to sort them, clean them. So these are some of the operations that are to be done before a recycled polymer is actually processed for further use. Okay. And then what are the pre-processing and processing conditions? What are the different temperature ranges for different polymers for recycling? Okay, because we get as a polymer, we may get as a polymer mix in the polymer waste. So we have to segregate, or if it is a combination of two polymers, we have to see the temperature of individual polymers processing, because if they are in a mixture, uh, one temperature may range may not suit the other. For example, one temperature range, if you choose some common temperature range for two polymers, one of the polymers may degrade in the temperature range, and other polymer may not even melt in that and cannot be processed in that temperature range. So we have to take a wise decision while choosing these operations and temperature ranges as well. Okay, and then what happens to the properties due to recycling of a single material? Okay, so here we saw that even if the polymer is recycled, if a single type of one type of a polymer is recycled, due to multiple recycling, there can be a degradation in properties, or there can be some properties like viscosity may also build up, which is not actually desired. So that can also happen. Again, there can be properties which start reducing. For example, an impact strength can fall down, can reduce from some value to due to multiple recycling. It can reduce to some other value which is not desirable. Similarly, viscosity can build up, which is not desirable as well for any particular use. So these were all discussed in this. The next lecture was on recycle up down cycling. This was again on sustainability. So waste handling in India. So what are the challenges? Because we get waste from different sources. It can be from household usage, polymeric waste, and then from industrial usage. So different kinds of sources can be there, and different polymeric combinations can be there. So what are those challenges? And additional challenges during mechanical recycling of polymers. Okay, because we have already seen that there are flow phenomena involved, rheological. So we have to consider those rheological properties, and then multi-phase is involved. So this is applicable even for a virgin polymer. So now what happens in case of a recycled polymer? Okay, so the complexities in transport phenomena, it gets added on. Not only that, the polymer processing also has its own complexities. For example, a dye swell may happen. So we know that to avoid dye swelling, or to get a proper size of a polymer in a extruder, we have to design the die according to that. So this is so with experience, we know that what would be the die size and all to be used, or and die shape and size. But we may not know the same for a recycled polymer. So this adds to further complex. Okay. And then there was a brief discussion on mechanical chemical recycling, and also a thought process on why can't we actually design materials or products or based on the properties of the recycled polymer materials itself, because recycling may have some impact on polymeric properties. So the virgin polymer and the recycled polymer may not have similar properties. So we have designs of products for virgin polymers, but why can't we but what we are trying to achieve is that to match the properties of recycled polymer to that of a virgin polymer for the same application. But why can't we think of some different application exclusively defined for a recycled polymer? So this thought process was given. And then uh, there was a discussion on upcycling through blending of polypropylene with LDPE, because both polypropylene and LDPE there is a reduction in properties as individual materials during service life and during recycling. But what if we blend these two materials and actually create material which has much better properties, even better than that of a virgin polypropylene? That was the thought process that was discussed in this. The next lecture again was on continuation of recycling, up down cycling. This is again on sustainability. So here there was a discussion on biocomposites. So using a combination of natural polymers with natural polymers or fibers, for example, cellulose, jute, along with the recycled polymers as a composite. And there was some discussion on with screw extruder and polymerization and molding process. So here there was a discussion on reaction injection molding, and then there was a discussion on resin transfer molding as well. Here a biocomposite of sandwich structure, a combination of soy based system was discussed in combination with natural fibers like jute, and then agricultural waste with the growing mycelia. So this agricultural waste with mycelia form the core, and your natural fibers like jute or cellulose form the fiber skin, and the soy based system form the resin. So this is how the biocomposite sandwich structure was made. So there was a small discussion on that. The next lecture was on flow behavior, rheology. An introduction to rheology was given. This was a concept based lecture. So here, polymeric fluid flow. So where do we find polymeric fluid flow? Do we find only during processing? No, even in products. So for example, a cosmetic product like your cream. So it has to spread, right? When you apply. So there is a fluid flow involved in that, or a jam, or a sauce. So here, even in products, polymeric products, or a paint, adhesive. So here, the flow of the polymer is very important in its performance. And similarly, flow of polymeric fluid flow is important during processing as well, both polymer manufacturing and composite manufacturing as well. So these were given an idea. And then the macromolecular inflow. So how are macromolecular systems classified based on flow behavior? They can be polymer solution, or polymer melt, or a polymer gel. It can be a physical cross-linking or a chemical cross-linking. And what are the mechanisms that affect the flow of macromolecular systems? For example, the segmental mobility will affect, entanglement will affect, cross-links will affect. So every aspect of it will have an impact. Interactions, whether it is van der Waals interaction or hydrogen bonding, hydrophobic interaction or ionic interaction, all these will have an impact on the flow of the macromolecular systems. So what are those parameters that affect the flow of macromolecular systems were discussed. Next, there was a discussion on non-Newtonian fluids. And then finally, a discussion on the flow scenarios. What is the response of macromolecules in certain flow scenarios, where it can be considered as just viscous dissipative material, and where it should be considered as a viscoelastic material. And next, what about, what happens in case of a presence of filler? So these aspects were all given an idea in this lecture. Lecture 76 was on cross-linking. This was again on uses. So cross-linkers for different polymeric systems. What are the different cross-linkers used in step growth polymerization, chain growth polymerization? So these were, examples were given for different set of polymers. And then extent of reaction for cross-linking. This was discussed especially on the step growth polymerization. And then cross-linking in rubber. So there was a discussion on cure time. Here, two trade tests, oscillating disk rheometer and moving die rheometer were discussed. And then cross-linking and gelation of in viscoelasticity and the Winter-Champion criteria was discussed. The final lecture of the week was on conversion of polymers. This was again on sustainability, conversion and combustion of polymeric materials. So, what are the chemical recycling methods? What are the factors that affect the conversion of macromolecules? The rate of conversion, the role of absorption and diffusion reactions were discussed. The next, there was a discussion on chemolysis of PET. Conversion, what are the different chemolysis techniques for conversion of PET to its monomers were discussed. And then there was a discussion on conversion to feedstock. And then finally, there was a discussion on combustion and incineration of polymeric materials. So these were, the brief recap of the lectures of week 10. Now let's get on to the practice assignment session. First question is, in a particular extrusion process, in order to get a rectangular extrusion profile, the die opening had the following shape. The rationale behind using a different complex shape die is, so in a particular extrusion process, in order to get a rectangular extruded profile, so the violet color indicates the extruded profile, the profile of the product material. Okay, how the shape of the product material was, it is rectangular, but the shape of die was complex. It is not rectangular, as you can see, it is of a complex shape. So why was this complex shape chosen to obtain a rectangular extrusion profile? Why not a rectangular die was chosen? This is the question. So why is it so? The answer is, this is due to the phenomena called die swelling. So what happens when actually the macromolecules are forced through a narrow opening, here in this case a die, a forced segmental stretching happens, and other operations at macromolecular level occurs. However, once the extruded comes out, once the product comes out of the extruder or from the die, there is a macromolecular recovery leading to conformations again changing back. Because we have already seen that macromolecules are viscoelastic. So there is a recovery due to the inherent elastic nature of the macromolecules. So this this is the reason, one of the major reason behind using a complex shape. There are also other factors such as surface tension of the macromolecule and surrounding air. The shape of the extruded profile is different from. So these actually, are the reasons why the shape of the extruded profile is different from that of the shape of the die. Or this is the reason behind using a different shape, complex shape, to obtain a rectangular extrusion profile. For example, in this case. So everything is based on the dice, is due to the die swelling phenomena and the macromolecular nature to recover back once it comes out of the die. Okay, because when it is passed through the narrow opening, the segmental stretching and other operations happens, and once it comes out, there is a recovery due to the inherent elastic nature and other factors like surface tension and surrounding air as well. So this is the reason why the shape of the extruded profile is different from that of the shape of the die. Now, next question. The diameter of a die of an extruder producing extrudate of diameter 2.4 mm with a die swell ratio of 2 is. So we just saw a question on that die swelling happens in case of extrusion. Okay, so the shape of the extruded profile is different from that of the shape of the die. So it's not only the shape, even this size, okay, can happen. That is why it is die swelling. Okay, both shape and size can differ from that of the die shapes. Okay, now here the question is, they have given that they have asked for the diameter of the die. When you want, when the extruded diameter, when the the product diameter is 2.4 and the die swell ratio is 2, so what will be the die diameter? This is what they have asked. So how do we solve? Die swell ratio is equal to extruded diameter by diameter of the die. Okay. So the product diameter divided by the diameter of the die gives the die swell ratio. Here what we have, we already have the die swell ratio. We have the extruded diameter. So what will be the diameter of the die? So die swell ratio is 2. Extruded diameter is 2.4. So diameter of the die is, it is die swell ratio, sorry, it's extruded diameter divided by the die swell ratio, that which is nothing but 2.4 divided by 2, that is 1.2 mm. That means what we can say is, see here is that when you use a die of 1.2 mm, there is a die swelling happening resulting in a product which is having a diameter of 2.4 mm. That means double the diameter of the die. Okay. Now let's see the next question. In twin screw extruder, dash screw helps in high pumping efficiency, while dash screw helps in high dispersion efficiency. So, is it for both the cases? Is it co-rotating screws, or is it co-rotating screws for high pumping efficiency and counter-rotating for high dispersion efficiency, or is it counter-rotating for both the cases, or is it counter-rotating screws for high pumping efficiency and co-rotating screws for high dispersion efficiency? Which of these is right? So the answer here is, it is actually co-rotating screws. It helps in high pumping efficiency, and counter-rotating screws help in high dispersion efficiency. Okay. So the answer is option 2. So co-rotating screws for high pumping efficiency and counter-rotating for high dispersion efficiency. Why is this so? Co-rotating screws leads to high pumping efficiency due to double transport option of the two screws. Okay. And similarly, counter-rotating screws, it leads to high efficiency of dispersion due to the calendering action between the two screws. Okay. So this is why co-rotating, it helps in pumping efficiency and counter-rotating helps in better dispersion. Okay. Now let's see the next question. Arrange the processing operations of polymers in the increasing order of their cycle time. Okay. So there are a set of polymer operations that are being given. We have to arrange them in the increasing order of their cycle time. So what are the options given is rotational molding, thermoforming, injection molding, compression molding, and blow molding. So 5 operations are given. Okay. Now we have to see and arrange them in the increasing order of their cycle time. Okay. So the answer is injection molding takes the shortest time. It takes only 2 to 10 seconds. Next is blow molding. Okay. Blow molding is used in bottle making. Okay. And this takes 10 to 15 seconds only. Next, thermoforming. Okay, it takes 1 minute. Uh, for example, it is used in making blister packing. Like, your tablets comes in a packing, right? So that is done through thermoforming. Those, with those holes and all, it comes, right? For placing each of the tablet. So that kind of a shaping operation is done by thermoforming, that takes 1 minute. And then compression molding takes 2 to 6 minutes. And finally, rotation molding takes 30 minutes. So we can see that, how fast is the polymer processing operation, and that is why it makes, polymers, used everywhere. So because your output is very huge, because your time to make one product is very very short. So that is why polymers, the cycle since the cycle time is very short, you can produce larger and larger quantities. That is why it is making this is one of the reasons for usage of polymers very extensively. Okay, next question. Dash is used for reduction of molar mass to achieve good flow behavior of rubber. So, is it stretching or blending, mastication or use of gas? Which of these is used for reduction of molar mass to achieve good flow behavior of rubber? The answer is mastication. Mastication is used for reduction of molar mass to achieve good flow behavior of rubber. Okay. Next, molecular dynamics deals with solving of dash balance or balances. So, what does molecular dynamics deals with? So, molecular dynamics, by the name, you know that it deals with molecules and atoms, right? So, if you think of molecules and atoms, you can think of their movement. That means what kind of equations are solved, what kind of governing equations are solved. It's actually your momentum balance. As I said, they are in movement. Okay. So, momentum balance equation uh, or Newton's second law of motion is solved for molecular dynamics. Next, divergence of velocity is zero for dash fluids. For which type of fluids is divergence of velocity zero? Answer is for incompressible fluids, divergence of velocity is zero. So we could see from this equation the divergence of velocity is zero for incompressible fluids. So incompressible fluids means the density is constant. Okay. So if you have the mass balance equation, so since the density is constant, so it does not vary with time. So we have the equation dou rho by dou t plus Vx into dou rho by dou x plus Vy into dou rho by dou y plus Vz into dou rho by dou z plus rho into dou Vx by dou x plus dou Vy by dou y plus dou Vz by dou z is equal to 0. That means there is a, so this term is the unsteady term, that is variation of density with respect to time, and this is variation of density with respect to space. So since density is constant, this entire term goes to 0. That means divergence of velocity is equal to 0 for incompressible fluids. Next, identify the viscous dissipation term in the below equation. So we have a equation here. Equation is given by rho Cp into dou T by dou T plus rho into V dot gradient of T is equal to kth into del square T plus sigma into your gradient of V. Okay. So, which of the terms in the below equation it represents the viscous dissipation term? The answer is the first term, it is actually internal energy accumulation. This is an energy balance equation. Okay. And the first term, and T represents, capital T represents your temperature, your Cp represents your specific heat, rho is the density, okay, and V is the velocity, and kth is the thermal conductivity. Okay, so the first term represents your internal energy accumulation term. The second term, since it's a gradient of velocity, velocity term is multiplied, right? So it's a convection. So it's a convection. There is a movement, right? So heat transfer due to movement of molecules. So this is a convection term. and this is a conduction term. Okay, uh, and uh, and the last term is your viscous dissipation term. Okay, this is a product of your stress and gradient of velocity, which is nothing but your strain rate. Okay, stress into strain rate will give you a dissipation, viscous dissipation. Okay, energy of viscous dissipation. So that is what is given here. Since it is a tensor equation, you have gradient of V. Okay, next. Recycling polymeric materials in the same application is open loop recycling. Is it true or false? So, recycling of polymeric materials in the same application is not open loop recycling. So, the statement is false. Recycling of polymeric materials in the same application is called as closed loop recycling. Okay, in the same application itself, it is reused. That means it is a closed loop. It's not going out of that particular factory, right? Within that same factory, they are recycling, so it's a closed loop recycling. Okay, the next question. Impact strength of high impact polystyrene dash after uh, 3 cycles of recycling, while viscosity dash after 100 cycles for LDPE. So, does it increase or decrease in both the cases? What happens to the impact strength after multiple recycling in case of high impact polystyrene, and what happens to the viscosity after multiple 100 times of recycling of LDPE? So the answer is the impact strength of high impact polystyrene decreases while the viscosity of LDPE increases with multiple recycling. It's actually not 3 cycles, it's actually 30 cycles in case of uh, in case of high impact polystyrene. So after 30 cycles, the impact strength actually reduces from 90 to 75 joule per meter in case of high impact polystyrene. Okay, and the viscosity for LDPE increases from 2000 to 13,000 pascal seconds after 100 cycles. Okay, next, according to Winter Chambon criteria, dash is independent of dash at the gel time. Which parameter is independent of which parameter at gel point or gel time, gelation time? Okay, according to Winter Chambon criteria. It is actually the tan delta. Okay, the dissipation factor is independent of the frequency at gel time. Okay, so gel time is nothing but a crossover point. Okay, this is the gelation time where the material changes from a more fluid like behavior to a more solid like behavior. Okay, so when we do it for different frequencies, what happens is that both the storage and loss modulus becomes the same function of frequency. So G prime is proportional to omega power n, G double prime is proportional to omega power n. Since both of those are same functions of omega power n, we know that tan delta, the dissipation factor, is G double prime by G prime. So that means both gets cancelled, omega power n by omega power n. That means it is independent of frequency. Okay, so what happens during a gelation process? So the relaxation time for a viscous liquid is nearly zero. That is, there is an instantaneous relaxation, whereas for a viscoelastic liquid there is a small relaxation, and as it moves and crosses the gel point, it becomes viscoelastic solid, where the relaxation time, at least one of the relaxation time, okay, of the gel point becomes infinity or very very large. Okay, and Winter Chambon criteria says that the dissipation factor or tan delta is independent of frequency at gel time. That means if you do the experiments for different frequency uh, and uh, you plot tan delta versus time, you will see that at gel point, uh, it is all these curves, they meet at one point. Okay, that means the gel time is constant even if you do the testing at different frequencies. Okay, now let's get on to the next question. Identify mechanical and chemical upcycling processes from the below. Replacement of cross-link in thermoset polymers, sorption and removal of volatile organic compounds. So we have to classify which is a mechanical recycling process and which is chemical recycling process. So the options given are both of them chemical upcycling, or are both or replacement of crosslink is in thermoset is a mechanical upcycling, and sorption and removal of volatile organic compound is a chemical upcycling, or is it option 3, replacement of crosslink in thermoset polymers is a chemical upcycling, while sorption and removal of volatile organic compounds is a mechanical upcycling, or is it option 4, both of them are mechanical recycling? Which of them is the right option? Answer is replacement of crosslinks in thermoset polymers is a chemical upcycling. Here, there is a change in the chemical, cross-linking, right? That means there is some chemical reaction that has to happen to replace the cross-link in thermoset polymer. That is why it is a chemical upcycling process. Whereas sorption and removal of volatile organic compounds is a mechanical upcycling process. Sorption processes are all mechanical process. Okay. Uh, so it is a mechanical upcycling process. So it is option C. A is chemical upcycling and B is mechanical upcycling. Okay. Now, the next question. Extent of reaction for cross-linking in step growth polymerization is directly proportional to the average functionality of the cross-linker. Is it true or false? Is the extent of reaction for cross-linking in step growth polymerization directly proportional to average functionality? How is the extent of reaction related to average functionality of the cross-linker? The given statement is actually false. So, for a monomer mixture with the average functionality Fm, the extent of reaction for a step growth polymerization, here it's given that the extent of reaction P is equal to 2 by Fm into 1 minus 1 by N. That means your extent of reaction P is inversely proportional to your functionality. Okay, the higher the functionality, that means you know uh, you need lesser cross linking for obtaining a 3D structure, right? To obtain a 3D network. For example, if the functionality is 2, the extent of cross linking required to obtain a 3D structure is 2 by 3. Okay, that is what is the meaning. Sorry, I'm sorry, if the functionality is 2, uh, it's 1. That means 100%, the crosslinker has to react with the polymer for crosslinking to happen. Whereas if the functionality is 3, then if 2/3 of reaction is done, then you will attain a 3D structure. Okay. So as the functionality increases from 2 to 3, you could see that 2/3, which is approximately 66% of if the extent of reaction is complete, you will achieve a 3D structure. Whereas the functionality is 2, you need 100% reaction for achieving a 3D structure. Okay. Next. In a pipeline, over a long distance, the constant area and with a constant flow rate, steady state flow. Polymeric material can be considered as dash, while in an extrusion or injection molding process through complex geometries with unsteady flow, polymeric material should be considered as dash. So, what kind of a behavior should be considered for a polymeric material in these two cases? So, in a pipeline, for a long distance pipeline, where the diameter of the pipe and the area of cross section of the pipe is constant and the flow rate is also constant, there is a steady state flow. Okay, that means the polymeric material can be considered as a viscous fluid. So only the viscous fluid uh, you know behavior can be considered, since there is a constant area and a steady state flow. So for solving this, we can assume the polymeric material as a viscous fluid. Okay. But in an extrusion process or injection molding process, there's a flow through complex geometries. With unsteady state flow, we have to consider polymer as viscoelastic material. We just saw die swell in case of extrusion. Here in extrusion, we have die swell. Why is the die swell? It is because of the inherent elasticity. That means we cannot consider polymer just as a viscous fluid, because viscous fluid means it does not have any elasticity within it. So if we start considering polymer as a viscous fluid in case of an extrusion or injection molding process, then you will not end up with the proper design of the extruder, right? And you will end up with die swelling and all. So only if we consider the elastic properties, okay, and consider the polymer as a, of course we have to consider flow also, the flow anticipative behavior also, because you have to flow and it is in a melt form. But still your elastic properties also has to be considered. That means you have to take the polymer as a viscoelastic material, so that we consider the issues like die swell and all, where elasticity plays a role, right? And you end up in a different shape of the product compared to the die shape. So so obviously you have to consider the polymer as a viscoelastic material, okay, where there are unsteady flow and complex geometries involved. Okay, now the next question. A continuous annular product is it produced by compression molding, extrusion, flow molding, or injection molding? In which of these processes a continuous annular product is produced? This is the GATE question, GATE 2014 question. Answer is extrusion. In extrusion, you will get a continuous annular product. Other processes like your compression molding, blow molding, injection molding, and all, they are not continuous process. Okay, one product has to come out, then the other product, the raw material for other product gets in. Okay, so in extrusion, continuously it can be extruded out. Okay, so extrusion is the process by which continuous annular product can be produced. Next, breathing operation is used for dash in dash processing technique. So, why do we use a breathing operation in polymer processing, and in which processing technique a breathing operation is used? Answer is breathing operation is used for minimizing the void generation or removal of gas or air entrapped, and it is used in compression molding. So, in compression molding, once once the mold is closed and then it is slightly opened, so I'm compressing, so mold is closed and compression operation is done, but the mold is slightly opened so that the voids and gas, and so the gases escapes, so there is no void generation. Okay, so breathing operation is used for minimizing the void generation and removal of gas or air entrapped, and it is used in compression molding process. Next, in polymers, due to their high viscosity, the mechanism of mixing is, what is the mechanism of mixing due to the high viscous nature of polymers? So, the mechanism of mixing due to the inherent high viscous nature of polymers is laminar mixing. That means layer by layer mixing only happens in case of polymers. You cannot have turbulence. Okay, you cannot have eddies or turbulence and all in case of polymer mixing. It's always one layer of polymer mixing with the other layer. It's a layer by layer mixing. So it's a laminar mixing in case of polymers due to their inherent high viscosity. Next. Viscosity of LDPE increases from 2000 to 13,000 Pascal seconds after 100 cycles of recycling. This is what we saw in one of the previous questions, that due to multiple recycling, LDPE viscosity increases. But what causes this increase in viscosity of LDPE? What is actually happening in LDPE due to multiple recycling process that leads to increase in its viscosity? The answer is cross-linking reaction can take place in LDPE, and this cross-linking leads to increase in molar mass, which subsequently leads to increasing in viscosity. Okay, so cross-linking reaction can take place in LDPE during multiple recycling process, and this causes increasing. Obviously, cross-linking builds up molar mass. Okay, your 3D network is formed, so there's a buildup of molar mass. So since there's a buildup of molar mass, obviously your viscosity is going to increase. Next, resin transfer molding is used for dash parts with dashed kind of kinetics. So what kind of parts, or what size of parts can be manufactured using resin transfer molding, and how should be the kinetics for this case? Answer is, resin transfer molding can be used for large composite parts. Why? Because the kinetics of cross-linking, okay, in case of resin transfer molding, the polymers chosen for this resin transfer molding, the kinetics of cross-linking and curing is slow. Okay, that is why you use a resin transfer molding uh, for large composite parts, because for the entire mold, the polymer has to flow and the cross linker has to be added, and then the reaction has to take place. You That means the kinetics, only for a slower kinetics, it's easier to make the large part. Otherwise, if it is going to, while adding your polymer and cross-linker, if it is going to start polymerization and cross-linking very spontaneously, then one part will be cross-linked and the other part may not be cross-linked properly, or before proper spreading itself, your cross-linking starts evenly spreading itself. Okay, so these kind of issues might happen. So that means a polymer with a slower cross-linking kinetics is used in resin transfer molding, and this helps in preparing large composite parts, for example, in aerospace application. Uh, Whereas if the polymerization kinetics is very fast, then reaction injection molding is used. Okay, next. This is a GATE 2019 question. Polystyrene coffee cup can be most economically manufactured by which of these methods? The most economic manufacturing method of polystyrene coffee cups. Is it thermoforming, or is it injection molding, or is it compression molding, or is it blow molding? Which of these methods is used for economical manufacturing of polystyrene coffee cups? The answer is thermoforming. Thermoforming is kind of a stamping operation. So this kind of an operation is used for making polystyrene coffee cups. Next, match the following polymer processing operation with respect to its typical range of shear rate. So the operations are compression molding, extrusion, calendering, injection molding. So the shear rates given are 1000 to 10,000 second inverse, 100 to 1000 second inverse, 1 to 10 second inverse, and 10 to 100 second inverse. So which of these operations have the particular shear rates? So four options are given. So is it P3 Q4 R2 S1 or P1 Q3 R2 S4 or P2 Q4 R3 S1 or P3 Q2 R1 S4? So what is the shear rates of each of these processes? Compression molding, extrusion, calendering, and injection molding. The range of shear rates for the following processes. Answer is compression molding. The typical range of shear rates is 1 to 10 second inverse. Whereas extrusion process, they have 10 to 100 second inverse. Calendering has 100 to 1000 second inverse. And injection molding, they have very high shear rates involved of the range of 1000 to 10,000 second inverse. So answer is option A, P3, P3, Q4 and R2 and S1. Okay. So this is a typical compression molding. So this is the mold and the the substrate is placed. Once you place the substrate, it is compressed. So the shear rates involved are, so in this process the shear rates involved are very less. It's just compressed. So there will be some flow and movement and all, but the shear rates involved in this, the deformation involved in this is very, shear rates involved is very small. Okay. And this is an extruder. So this figure you would have seen in polymer processing lecture 2, I guess. So this involves, there is a flow of polymer through the screws and out through the die, right? So here, multiple parameters. Your diameter of these screws is helix angle. So these parameters, they play a role. And here the typical rates, shear rates involved is 10 to 100. In calendering operation, you could see, the polymer passes through rolls. So comparatively higher shear rates are involved. Okay, especially here it is a counter movement. So higher shear rates are involved. And finally, in injection molding, so we could see that complex structures can be prepared using injection molding. So where the diameter is or the length of the section is very, very small. The shear rates, it depends on both the diameter of that particular section as well as the flow rate of the polymer melt, right? It is velocity by distance, right? So obviously, if the distance is smaller and smaller, that means even for a constant velocity, the shear rate will be, or the strain rate will be very high. So that is why, your injection molding has very high shear rates. Okay. Especially when you just pass the polymer melt through very small openings and all, okay, of the mold cavity. Okay. Hope you understood. Now let's see the next question. Identify if the statement is true or false. For macromolecules having diffusion constraints, the conversion reaction happens through reactions confined to surface and gradually the reaction front proceeds inside. Is it true? Is it true that for macromolecules that are having diffusion constraints, the conversion reaction happens through uh, reactions confined to surface, and then slowly the reaction friends proceeds to inside? It is true. So, uh, this was discussed in factors affecting conversion of macromolecules. So, when there are diffusion constraints, what happens is that since the molecules, the small molecules for reaction, polymeric reaction to, to react with the for converting the macromolecules, for breaking down the macromolecules, for example, they may not be able to diffuse through bulk of macromolecule, but they may be on the surface. So first those molecules interact with the surface and the reaction starts here, and slowly this builds on. Okay, this reaction proceeds towards inside also. So first inside there will be no reaction, so there will be reaction in the front on the surface only, and then this moves further inside step by step. Okay, once this front side reaction is done, then the molecule starts diffusing to the inner portion. So this is what it was discussed during dissolution and recovery of macromolecules also in previous week's lecture, where for a glassy amorphous macromolecule, the solvent, you have different sections. For example, for the innermost will be glassy, and then the next to it will be a rubbery, and then next to it will be a gel like structure, where there is a large amount of solvent, and finally in the solvent bulk there will be high concentration of polymer molecules also. Okay, that is how the dissolution happens. Okay, so and that is how it happens. Whereas if there are no diffusion constraints, then the reaction happens everywhere. So bulk reaction happens. So the material has no diffusion constraints, so it can diffuse through the entire macromolecule, the entire film, and the reaction happens everywhere. Okay, next, and the final question for the week. So multifunctional amines are used as common cross-linkers for epoxy. Is it true or false? So we had lecture 76 was on cross-linkers, where different cross-linkers for different types of polymers were discussed. Okay, in the beginning of the lecture. Okay, for step growth polymerization and chain growth polymerization. So the question is from that. So multifunctional amines are used as common cross-linkers for epoxy. Is it true or is it false? The answer is true. Yes, multifunctional amines are used for epoxy. So for step growth polymerization, for example, Rizol, there's a thermal cross-linking through dehydration that is happening. And for materials like Novalac, urea formaldehyde, and epoxy, multifunctional amines, for example, diethylene triamine or hexamethylene tetramine are used. In case of chain growth polymerization, for polydienes, for polybutadiene, butyl lithium is used. And then for polyethylene, chemical thermal or radiation is used. In case of chemical, dicumyl peroxide, peroxides are used. Okay. So that's it with the practice assignment questions. Hope you were able to follow the practice assignment questions. So thank you all. Have a great evening.